right, guys, we're going to continue on with the chemical reactions in organic chemistry. All right. So, Alkene, did you know that you're on video?
Yeah, I was texting my dad.
Oh, my. Oh, okay. Okay.
My mom drinks white, so I can't text her.
Oh, okay. All right, so we got alkanes substitution reactions. All right. So give the structures and names of the monosubstituted products for the reaction of propane with bromine. Let's see. Okay, I got a couple down here. We got this. Oh, okay. I was going to say, where's the reaction? Oh, it's written in the words. All right. Oh, man. Reaction of propane. Sorry, that's probably the product. So we got propane plus bromine. Give the structures and names of the monosubstituted. So, what are the different, basically, not allotropes, but the isomers that could be formed? We could have a bromine that could be on a primary carbon, or we could have a secondary carbon. You got it. We'll just get rid of that and put it here. And then, does it say name them? Oh, structures and names. Okay, let's name it. So this one is what? You got 2-bromopropane, and this is just 1, 2, 3. Oh, yep, I do. So this is bromopropane. Bromopropane. That's a P. Oh, where does the other bromine go? So this is a substitution reaction. So we're substituting one bromine for one hydrogen. So then it's going to form, but yeah, that's a good point. HBr is going to be one of the products. So as you can see, organic chemistry is all about creating mixtures and then separating those mixtures. So you could have potentially, all three of those products produced. And then what if you wanted to isolate one over the others, then you'd have to do a process to separate them out. And that's what takes so long in the organic chemistry lab. All right, if we were reacting propane with chlorine, we should get more of isomer A. However, we get an equal mixture of isomer A and B. We're reacting propane with chlorine. Okay, so isomer, we'll call this one isomer A, and this one isomer B. So if you had chlorine, you'd be more of the secondary haloalkane, but you get an equal mixture of A and B. So if we react propane with bromine, most products will be isomer B, reasons beyond this course. So essentially you're not going to be asked to state which one it is or explain why in an IB type question. All right, so here we got there it is. Yeah, so these are the what we wrote over here. Okay. Moving on to the next one. Alkene addition. So basically the main idea is when you're reacting a halogen with an alkane, you're going to form a haloalkane plus HBr or HCl, which is hydrogen halide essentially. So then we got alkene addition reactions. There it is. And you're starting with a double bond and you are adding things. So whenever you start with a double bond, it's probably going to be an addition reaction. And here we got a hydrogenation, like hydrogenated palm oil, stuff like that. It is where you have double bonded, basically oils or fats that are unsaturated, found from plant matter. And what they do is they add hydrogens to it. And they have to have a nickel catalyst and at high temperatures, and this is how they make margarine. Oh, that's what we talk about right here. I can't believe it's not butter. So they make it out of vegetable oil, basically, and they add hydrogen. Could it cause cancer? Maybe. I think it is FDA approved.
Yeah.
So, okay. So then it probably doesn't. Yeah, we should do it, yeah. It's always safer to go natural if you can, but... All right. So, what's going to happen is the H's are going to land right on top of the double bond. We're going to have something like this. I'm just writing it all out because it's a small molecule, so pretty much just the double bond disappears. It's called a hydrogenation reaction. Keyword, nickel. So you got to have nickel catalyst with a high temperature. Isn't that right, Ben? Yeah. What's the catalyst? Anybody know what the Ben? Do you know the catalyst?
Ben knows, actually.
Yeah, Ben knows the catalyst. What's the catalyst? Ah. Oh, did you say nickel?
What?
Oh, nickel. All right. All right. Yeah.
It's on my paper.
It is.
And it's right there.
All right. We're going popcorn read on this. Alessandra gets the pick she left off.
Pick whatever this guy's name is.
Oh my god, no. Natalie.
Hurry. Back in the 1950s, it was recognized that vegetable oils could be substituted for animal fats, such as in butter, by making a product we know.
Right here is a picture of a fatty acid. We got double bonds, and we are basically taking some of those bonds out, adding nickel as a catalyst and hydrogen. So, and what's the difference between butter and margarine? Well, yeah, I can't. There's like hardly any difference. So, butter is made out of animal fat, and margarine is made out of vegetable byproducts or vegetable oil. But vegetable oil, unsaturated fats are going to be more runny and liquidy. So you can't put liquid on your bread. It's got to be like semi-solid. You can.
I prefer when it melts, actually.
Yeah.
Oh my god, melted butter on like zucchini bread or banana bread.
Yes.
Yeah, but how do you'd have to spoon it on, I guess. I guess you could
That's
spoon
fine.
it
Yeah.
on. Yeah. That's true. But if it was liquidy, then you could believe it wasn't butter. So we got to be able to have the slogan work. So. Well, another reason, margarine has a longer shelf life than butter. Butter's going to spoil a lot quicker. So that's another reason margarine was made. So you can ship it, you can use it in the military, you can store it for a long time. So there's a lot of benefits. All right. Alkene addition reactions, halogenation. So this is similar to hydrogenation, only instead of a hydrogen, it's a halogen that's being added. So we got propene, which looks like this, and we're adding bromine. What product forms? And it's Br2 because it's a diatomic element. For this one, you do not. No. So this is going to be pretty spontaneous. You got a double bond, and then a halogen is going to react pretty readily. And we're just adding bromines onto it, but I got to make sure I don't lose a carbon. And there you go. And this is going to be what? 1,2 dibromo propane? All right. We got example 2, cyclohexene. There we go, double bond, and we want to add chlorine. And if you didn't show the 3 dimensions, it would be fine. But when you got a shaded triangle, that means it's poking into the paper. And if you got a dashed triangle, it's popping out, like a pop-out book. And the reason you're doing that is because these chlorines, they want to be as far apart from each other as possible. Alright, and there is a specific reaction mechanism, but IB doesn't need you to know that. I'm just going to focus on the ones that IB does need you to know, the SN1, SN2, which we'll get to. Because there's enough to take in as it is. Alright, here we got alkene addition reactions, hydrogen halide. So we did hydrogen, hydrogenation. We did halogen, halogenation, and now there's hydrogen halide. Alright, so ethene. I'm just going to write the whole thing out. Oh my gosh, there we go. Alright, and this one's a little bit tricky because hydrogen halide is HCl. The other one was simple because it's 2 H's or 2 Cl's. So you just plop them on, but which one goes where? And I guess this is a poor example because we're talking about ethene, so again, it doesn't matter. So we'll do a better example after this one. Because whether you got the chlorine on the left side or on the right side, it doesn't matter because if you flip it, then it's still on the left side or the right side. Alright, but what happens if we got something like propene? So, yeah, propene, now we got something where the Br could either be on the center carbon, the secondary carbon, or it could be on the primary carbon. We're not sure. That's where we gotta get some help from this Russian guy called Markovnikov's. Can anyone say that 5 times fast?
Markovnikov.
Yeah, you could do it. Wow. I probably couldn't do that. All right, Markovnikov. I'm going to have struggles with saying that 1 time slow. Says that a hydrogen will attach to the carbon that is already bonded to the greater number of hydrogens. All right, so we got to think which carbon is, well, no, we forget about that one. We're looking just at the double bond. Which one is bonded to the greater number of hydrogens? Is it this one that's bonded to 2 hydrogens or this one that's bonded to 1 hydrogen?
Well, it's bonded to 2, probably.
Yeah, the one that's bonded to 2.
Nice.
All right, so we're going to add HBr to this. And it's going to form a product, and the hydrogen will attach to the carbon that's already bonded to the greater number of hydrogens. So that's going to be this primary carbon is going to add a hydrogen, and then this secondary is going to get the bromine. And according to Markovnikov's rule, that should be the product. So 2-bromo-propane. Ethene, it didn't matter because it's so small. So why don't we do one more example? Let's say we've got, I don't know, someone throw a molecule out there. Pentene. 1, 2, 3, 4, 5. You don't. We're not going to ever be dealing with addition reactions with alkynes. We don't have to worry about that. So it's a little bit of different stuff going on there. Let's see. Why don't we do this?
2-pentene.
Yeah, 2-pentene. All right. So, okay, this one's a little bit trickier. Let's do HCl. That's a hydrogen halide. And we want to add the hydrogen to the one that has the more hydrogens already. Well, here we got 1, here we got 1, so what we got to do is look at the chain as a whole. So technically we got 1, 2, 3, 4, and then here we got 1, 2, 3, 4, 5, 6. Yeah, so then we'll go with this side being the one that has more hydrogens, therefore we add the hydrogen here, and over here is going to be the chlorine. So that's kind of a little different spin. So if they are equal, then you got to look at overall chain that goes with them. And that should be, this is what, 2-chloropentane. Yeah, 2-chloropentane. All right, moving on. Hey, we got some more addition reactions. So far, we did hydrogenation with H2 added. We had halogenation with a halogen added, like Cl2 or Br2. And we had a hydrogen halide addition, which is like HCl, HBr. And now we got hydration. Hydration, that's like water, right? You are hydrating it, you are adding water. All right. So, let's see. Draw the hydration of ethene. We're doing this small one again. You could write ethene like that, but that looks like an equal sign, so I don't want to confuse people. All right, and then we're adding water. So hydration is just add water. But it's not going to do anything unless you have a catalyst. And the catalyst required is sulfuric acid. So I'm going to put that right above the arrow to show it's a catalyst, not consumed in the reaction. And for this one, we're going to have the double bond be gone. And really, it doesn't matter. Oh, what does H2O split up into? OH and H. You got it. OH and H. So we got the H's. So this is how you make an alcohol. You hydrate an alkene, or this is one possible way. All right, so that one, it didn't matter which side the OH went on. So, but what have you got? Butene. 1, 2, 3, 4. All right, so now we're going to add water. And we're going to need some help from Markovnikov on this one, I think. So, which one has more H's?
Farthest to the right.
Probably this one, yeah. Oh, left, right, yeah. Actually, so for this one, if you're looking at bond to bond, it's going to be this one.
So we have to view where the double bond is?
Yeah, unless they're equal, then you look at the others. So for this one, the H is going to be added to the side, and the OH is going to be added on the second carbon. Oh, I forgot to write my catalyst, H2SO4. Are you going to want to remember that? Yes. H2SO4 is the catalyst for hydration. And what's the catalyst for hydrogenation? Nickel, and a high temperature. Nickel and high temperature. All right, so we're going to be practicing those. Those are addition reactions. You're going to enjoy this. Is there the reverse where you could eliminate and form an alkene?
Yes.
Yes, but IB eliminated that from the curriculum.
Yes.
Yay.
So we're not going to focus on those. But it would be the reverse. All right, polymerization of alkenes. So basically polymerization is making a continuous repeating chain of a specific, what's called a monomer, which is a basic unit. So an example of a monomer could be just, a CH2 component. And then it repeats CH2, CH2, CH2. And this is huge in organic. Nylon is made out of polymers. Foam insulation is made out of polymers. Lots of different plastics. Polyester. So all of the clothing we wear is a polymer. We're pretty much wearing ancient organisms, which is plastic is a polymer that's made out of.
Styrofoam is, right?
Styrofoam's a polymer. So
That's
we live
how
in.
the napalm ties in.
That's a polymer, yep. We live in a polymer world. Fun fact. It only takes, I think, 2 minutes for you to not be able to get out of your house when it burns down. So, like, if you have a fire, you got, like, 2 minutes. Back in the day, in the 1950s, you had, like, at least 15 plus minutes. What's the difference? In the 1950s, stuff was made out of wood. And nowadays, stuff's all made out of plastic. Your couch, your clothing, your carpet, it just goes up in flames instantly. So, you want to have smoke detectors if you can get them. Yeah, don't have a fire in 2021 for sure.
Yeah, I need them.
All right.
Or we'll just that'd be more fun. Make the situation better. You guys swap. Oh.
All right.
Sounds much better.
So alkene used in polymerization reaction is called a monomer. So it's a basic unit. And a polymer is a long chain of those basic units. And here's some more examples. Many uses in industry. Ethane polymerizes to form polyethylene. Hey, think Walmart plastic bags. Polyethylene. So anything made out of plastic. Discovered during World War II and used in the development of radar, containers, and piping. So lots of stuff. PVC piping, that's huge. So nowadays it's all of our piping for plumbing is PVC. It's really durable and it's cheap. Unlike galvanized pipe, which after 60 years clogs and then you gotta pay $500 for a plumber to help you out. Huh. And now they got the flexi hose. It's basically like a garden hose, it looks like.
Flex seal.
Flex seal, there you go.
What is flex? Is flex seal made out of polymers?
Polymers, yep. So you go to Home Depot,
You can
there's
spray
Everything
polymers.
you buy.
everything you buy has got polymers.
Oh, okay.
So there's so much polymer in our products that they found out that in the human fecal matter, there's trace amounts of plastic polymers. And they found every single place on Earth, even in Antarctica, see some plastic polymers. So we're kind of killing ourselves through plastic, unfortunately.
You already are saying that.
Oh, and there are environmental groups pushing for global phase-outs. Just straws from McDonald's do terrible things. You see the video about the sea turtle with a straw in its nostril? It's terrible. Let's play, yeah, let's watch it.
I have I usually do, but if I were ever,
All right. So I want to get through basic. We got combustion of alcohols, but then also the oxidation of alcohols, and then we'll have some time to practice this. So, hey, I remember a couple of days ago we did combustion of alkanes. Elson, do you remember that? Combustion of alkanes? Yeah, that produces carbon dioxide and carbon monoxide. If it's, what would we call it? Complete and incomplete. There we go. Well, we got combustion of alcohols because we all know that if you have like rubbing alcohol and you light it, it probably burns. It does. So it's the same thing. It's a combustion reaction. Alcohol plus oxygen produce CO2, water, and energy. Oh, hey, ethanol. That comes from corn byproduct, and it's put into our gasoline. So, nice. And I think it lowers the price of gas a little bit. Yeah, it's usually on the cheaper side. But it raises the price of food, so that's the downside. What do we got here? Oh, here's an example. What is this? This is pentanol. Pentanol and oxygen reacts to form CO2 and water. All right, well, let's do an example problem of this. So, what's this going to produce? We got 1, 2, 3 carbons. Oh, wait, it always produces what 2 molecules? Carbon dioxide and water. We're doing complete. All right. And I got 3 of these carbons, so I'm going to need a nice big 3 in front of the CO2. I've got 1 of these H's. Oh, man. So, we'll have to put a 2. We need 2 of these guys. That means we're going to need 6 of those. That's a 6. And we're going to need 4 oxygens. No. Oh my gosh. I'm going to have to rewrite all of those coefficients. Oh, are we good? Oh, perfect. There we go. Oh, whew. All right. But no, we got 2 O's here.
Uh-oh. On the left for the...
Darn.
Wait, what?
All right. Help me out here.
So it's
Do we need 8 H2Os?
I think so.
The first coefficient's got to be 1?
Uh-huh.
Right here?
Yeah.
But then you got 1, 2, 3. Oh, the H's. Oh my gosh. See, I'm not writing it out here. Let's just write this out. 1, 2, 3. We got 3, 4, 5, 6, 7, 8.
Oh.
Where'd you get oh.
There we go. There we go. Yeah, for balancing, you just might want to write the molecular formula, I guess. That might be easier. Okay, so we got 8, and Alia's right. We're going to need a 4 here. Going to need a 4 there to get our 8 hydrogens that we want. That gives us 4.
That should be a 3, right?
Let's get rid of this.
3 CO2.
And 5 O2. There we go.
Wait, what
So-
about that OH on the left? Oh, right there.
Double everything and then
You gotta double it.
Got to double everything, yeah.
Oh, boy.
what is happening?
Why can we not balance?
You lost me.
All right, so we need 10. .5 here, right? 9. So 4.5 times 2 is 9, plus this one is 10. Then we double everything. Whew.
Should be 9.
Yeah, I'm going to rewrite it. There we go. That was kind of a little advanced in the balancing area. Yeah. So that is balancing, what do you call it? Combustion of an alcohol reaction. Let's see. So more mass of the alcohol, of course, more energy released. Carbon monoxide, when oxygen is scarce, is produced. Here's an example. Okay. Yeah, I was getting confused. I was like, what does this have to do with combustion of alcohol? Oh, it doesn't have anything to do with that. So, oxidation of alcohol, that refers to what we're doing right here. This is kind of just a summary lead up to the next couple of pages where we got primary alcohol, secondary alcohol, tertiary, which is based off of which carbon is the OH hanging off of the end, the middle, or a branch. So oxidation of alcohol oxidizes carbon attached to the OH. Heat is required as a catalyst, and aldehyde is separated by boiling points. Lower the boiling point, the aldehyde will separate. And then a carboxylic acid is formed by prolonged reaction under reflux. So what we got right here, this is a reflux apparatus. And what we got is a tube inside a tube. The outside of the tube is hooked up to a hose where water goes in to cool it off. So basically, oh my gosh, you can't see it. Sorry about that. So basically, this is kind of like a distillation apparatus without collecting the pure water in another chamber. What it does is it heats up this little reaction right here, and it vaporizes. But then it's cooled by the outside tube filled with cool water. And then it condenses. So it's also called a condenser or a reflux apparatus, and it falls back down to react further. So it's a way for it to keep on reacting even though it's evaporating out. The only difference between this and a distillation apparatus is this would be hooked up to another tube where you collect the water that's pure. So, yeah, that's pretty much that. If you got a primary alcohol, oh, that's not it, sorry. Oh, here it is right here. Yeah, the primary alcohol is going to form basically an aldehyde. But then if you continue to react it, it's going to form a carboxylic acid. That's only primary. Only primary. So anybody know if you heat up a primary alcohol under reflux, what's it going to produce? In aldehyde. But then if you continue to heat it under reflux, what does it form? Carboxylic acid. You got it. So I would circle this. So a primary alcohol heated under reflux forms the aldehyde. If you continue to heat it under reflux, it forms a carboxylic acid, essentially. But what happens if you have a secondary alcohol? Oh,
The ketone.
it forms a ketone. You got it.
That's correct.
So secondary is where it's in the middle of the chain. Secondary alcohol, the OH. And then tertiary is no reaction. So if the alcohol is on a carbon that's on a branch, then it's not going to react. It's not going to do anything. And important to know, we got the tertiary will not change color when you add potassium dichromate, which is an indicator. But when you add it to a primary or secondary, it will turn, I believe, green is the color. Does it say on here? It doesn't say. Okay, so this color is green. That one's green too. Trouble with black and white, all right. And this is yellow. So that's going to be key. You're pretty good chance in May you're going to have a question involving this. This is one of those explanation point concepts that they want you to know. It's definitely going to be on the unit exam in this class. So you got primary alcohol under reflux will turn into an aldehyde. Continued under reflux, it turns into carboxylic acid. And if you add that little thing called potassium dichromate, which is yellow, it's going to turn what color? Green in the presence of an aldehyde and a carboxylic acid. Or a ketone, because it's looking for that carbonyl. But if you have tertiary, what happens? Nothing, and the color of potassium dichromate stays yellow. All right, good. So we're going to do some practice with that tomorrow, but I think that's all we got time for.